All right, let's get started. It's my pleasure today to introduce to you the illustrious Andrej Bogdanov. So Andrej right now is a professor at the University of Ottawa. Before that, he was faculty for many years at the Chinese University of Hong Kong until 2023. Before that, so he did his bachelor's degree and master's degree at MIT, followed by PhD at UC Berkeley. Postdoctoral work in a number of places, including IES, Tsinghua, and Rutgers University, the DIMACS. He's been a visiting professor of a number of places. I noticed on your website you did not include the Fact Center in Israel, so even more places. Andrej's research is really at a fascinating area, kind of the overlap of complexity theory and cryptography. He really looks down at the fundamentals, things like how complex is it to do objects like secret sharing, like pseudo-randomness. His work has gone all over, both, I was talking with Alon earlier, both looking at the simplest objects and trying to make them simpler, and yet simultaneously looking at hard objects with hardness amplification. I don't know if you've heard this epic story about Andrej going into Israel airline security, where they pulled him to the side, asked him very interestedly about his research before he could, enter or leave the country of Israel. And he explained to them he does hardness amplification. He takes hard problems and makes them harder. They said, "No, you mean make them easier?" I said, no, harder. And how long were you detained by security? 3 hours, yes. So they had a lot of time to talk about his hard research. So even more recently, Andrej's research has gone across other very fascinating areas, continuous LWE. There's a very interesting TCC talk coming up, I believe, on Thursday. Actually, I should know the program better than I do. And he'll also be speaking today about recent ties of his research with statistical physics. So Andrej, we are very much looking forward to hearing more from you.
Thank you, Elette, and there is no way I can deliver after that introduction, but I will do my best. So I want to start with a confession, and the confession is that this is the first time I came to Milan was in 2019. Soon after, Luca Trevisan started in the department here, and now I cannot even count anymore, my 5th or 6th time in Milan, and I should probably add that to the places about where I have been visiting. And it's every single time it has been so much fun, and Milan is a great city, but I have yet to see like the big sights of Milan because, well, it's also hard to score tickets for these things, but it's been, people at Bocconi have been keeping me busy. Luca Trevisan was my advisor. I started doing work in complexity theory. First time I prepared a talk, and of course I had too many slides, and I tried to talk too fast, and well, I started with the outline, and he said, well, you should never start your talk with an outline, because they will be listening to you blubber for an hour, so why do you have to tell them what you're going to tell them, like one more time? And I never put an outline in my talk, but today I feel compelled to break the rule, and this is my real confession, so now I'm going to make Mohammed and Elette regret their invitation, is that there is not going to be much new crypto in this talk, but I find it very interesting what I want to tell you. And the reason I mean... But or hence? No, but no. And the reason I find it interesting is I want to tell you about some of the things that I've been learning in the last few years, much of it through collaborating with people here at Bocconi, about computational hardness, right? And different ways of viewing what it means for a problem to be easy and for a problem to be hard. And, so let's start with the way that we usually set up things, right? We're very happy with our theories, right? And we all start with this guy, right, Turing. And Turing was such a leading figure. He had so many insights about, well, he had few insights, but few very powerful insights about computation. But if I had to summarize, like the one thing that Turing said that the insight that he had that makes our work easier and possible at all is that I think his main insight is that there is one algorithm, right? There is one algorithm. The Turing machine is the one algorithm. And that's really kind of simplifies conceptually the thinking, especially in cryptography, where we worry the adversary can be any possible algorithm, and algorithms are chaos, right? How can you worry about all of them at the same time? And Turing says, no, you don't. You just worry about the Turing machine. That's all you have to do. And the reason that's such a powerful way of thinking is because it lets us kind of organize the different ways that we think about computation, and it has led to beautiful areas like complexity theory, right? And the whole kind of, the reason that we teach it and we set it up in ways we do, right? We talk about complexity classes, but when we say a complexity class like NP or P-space or closer to crypto statistical zero knowledge, really what we mean is an algorithm, right? NP is brute force search, right? And P-space is like games even like the way that the subject is set up is a lot of the time that's the intuition. So, we always get mad at students that confuse with NP and NP completeness, but in some way that's the point, right? We want NP to be about NP complete problems. And the reason we can do that, at least in the world of worst case complexity, is because it's been very successful, right? You come up with a random question, you try your basic algorithms, you say those don't work, you scratch your head a little bit, next thing you know, well, let's prove it's NP complete. And it works a lot of the time, right? Not always, but if you come up with a random question for which you cannot design a worst-case algorithm, you can handle it using the tools of worst-case complexity. But then, like the insight that cryptographers had, or even before there was cryptography in the 70s and the 80s, is that to do crypto, we don't, worst case complexity is just not enough. We need to start thinking about average case complexity. And I think initially when people started working at it, we had this kind of idea that the kind of order we have in worst case complexity, we should also have it in average case complexity. And like Levin came up with this notion of average case complete problems, and like there was this parallel theory. And for a long time, we've been looking for ways to make the theory work in the average case. And there have been successes. Clearly, there have been successes, many of them relevant to crypto, and I didn't put them here, right? So our favorite problem, like LWE, DDH to a certain extent, they're based on these ways of looking at it from a complexity theoretic lens and say, what do they reduce from, what do they reduce to, and using this to argue hardness. This works, to a certain extent, but, it's somehow, it captures kind of the things that we know how to do, but there's so many things that we don't know how to do, and thing is, it's very brittle. In worst case complexity, like you set things up and that's it, but in average case complexity, there are so many different ways in which you can play. You can play with the distribution, you can play with other parameters, you can ask search, decision, all these things. They don't relate to one another so nicely. And I think by now, right, somehow we feel like when there is a reduction between average case problems and they exist, they're the exception rather than the rule, and they're extremely hard to find. And tomorrow you'll hear from my co-invited speaker, Shuichi Hirahara, who has been like one of the people who do this brave work of finding average case reductions, but not all of us can do that. It's hard work, and a lot of time it fails. And the other thing is that now, like in the age of machine learning and statistics, and there is this whole like slew of new kind of average case problems that come about our way. And I wrote some of the names here, so this is just like name dropping, right? There is spiked tensors, Sherrington-Kirkpatrick Hamiltonians, hyperloops, sparse recovery, stochastic block model, blah, blah, blah. And you try to put order in those, and no, they're kind of little islands. We don't really know how to relate them to one another. And again, like I'm oversimplifying things, there have been some successes, but the point I want to make is that I think having like reductions between average case problems is the exception and rather than the rule. And the fact that there are no reductions, I think by now, it could be that we're not smart enough to find them, which is what the complexity theorists want us to believe, but it could be that they just don't exist and that we have to look for something else. And what I want to talk about today is about some of these alternative ways of talking about average case hardness. And the starting point is that in the end, like our adversary is the algorithm. So we want to talk about, what are these algorithms that we're trying to fight against when we're trying to show that these problems are hard. And, Turing had this idea that there is one algorithm, but, once you start getting into like the details and start probing things, you realize that there are many algorithms, right? And that you have to handle them all. And what I want to advocate for today, and that's something that I've kind of tried to say for many years, again, it's an oversimplification, but I think it's a useful one, is that maybe there is not one algorithm, but there are two algorithms. Okay? And what are these two algorithms? Well, there is gradient descent, and there is Gaussian elimination. Those are the two algorithms, right? And as long as we can handle those, we should be pretty happy, right? And the reason they're like not one but two algorithms is that these are kind of very different, right? So when you try to kind of come up with words to describe them, we come up with something very different. So gradient descent is like a smooth, robust algorithm. You would be using words that you used to describe like wine, right? It's like something that works like this. And on the other hand, Gaussian elimination is different. Like it's very kind of intolerant. It's exacting. It's like a German-style algorithm, right? You change things a bit and no forgiveness there, right? So like why is this useful to think about it this way for crypto? Is, well, in some sense, we can think about those and we can say, well, how do we design our crypto to resist Gaussian elimination, and how do we design it to resist gradient descent? So, and we kind of understand how to do these things at some level, right? So we know that to resist the Gaussian elimination, we add noise, right? That's been kind of the main thing going on in crypto in the last 20 years now, right? We fight Gaussian elimination as noise. And what do we fight gradient descent with? Well, we fight it with some kind of like bounded independence or whatever, and it doesn't matter if you don't know what I mean, because today I want to focus on the first algorithm. I want to claim that we know how to handle Gaussian elimination. There's exacting, we just make things a bit, shake them up a bit, and I want to focus on gradient descent. Because in some sense, we are in the age of gradient descent. That's the powerful algorithm these days. That's what machine learning people use, and that's the one that we want to understand. So I want to talk to you today about two kinds of methods, or two, like, I guess, frameworks for thinking about hardness for algorithm for gradient descent and gradient descent-like algorithms. So first of all, we have to have some model about like what do these algorithms do, and what do we mean by smooth and robust? Well, one way of thinking about it is that something is smooth, an algorithm is smooth intuitively, is that an algorithm takes an input and produces the output. We want to change that if we change the input by a little bit, then the output is going to change by a little bit. So that's kind of the intuitive notion of smoothness that we have. And then we can ask sort of how do we model this? Like what would be the kinds of algorithms of computations that have these properties? And these are good to keep in mind sort of to when we think about what the adversary does, and they will play a role in the methodologies that I will try to describe to you. And by the way, I have to apologize, I'm far from an expert on this, I'm a learner, but I think I come a bit from the crypto angle, so I hope that I can make it more relatable at least. So one is a low-degree polynomial, but these are not our usual polynomials over finite fields. These are now polynomials over real numbers, right? And polynomials have the property that if I change x1 by 0.01, then y is not going to change by very much, right? That's what we learned in calculus when we go to school, right? So that's one example. Another kind of example that's kind of closer to, what some of us are working on is local algorithms. So what does local mean, right? I have a bunch of inputs and I have a bunch of outputs. And we can talk about both input locality, meaning that if I change every input does not affect too many outputs. So if I change an input, there are only so many outputs it can affect. Or output locality, it's a bit more complicated. It goes in the other direction, but we'll talk about both. And then, if you come from complexity, then there is kind of the next level of algorithms, which is bounded depth circuits, where you start with some inputs, and then you do some layers of simple calculations, like AND and OR gates. I wrote plus and times, but let's think about it as AND and OR, if they're bits. And then after doing like 5 or some small number of layers of calculation, you come up with the output. And, like it was understood in the 80s that what makes this computation special is precisely this smoothness, but they possess this smoothness property on the average case, that if I take a random input and say I flip a bit in the random input, the output bit is quite unlikely to change the answer. So those are kind of the model algorithms that I want to keep in mind. And now I want to do 2 examples, and this business is fun because we can do calculations. So I'm hoping to show you some of these calculations. So the first method that I want to tell you about is what's called the low-degree method, or low-degree analysis. And this is a method for arguing, like in some restricted way, that 2 distributions are indistinguishable, right? So it's a basic thing that we want to do in cryptography. And the example that I want to show you is the planted click problem. So what is planted click? In planted click, we either have a random graph, that's the null distribution. We have n vertices, and every edge is present with probability 1/2. Or we have a random graph with a planted click inside. So I take a subset of k vertices at random, and then I connect them all up in a click. And this has been, something that people have been wondering about for a long time, right? We know that when the click is relatively small, it seems to be, you can detect it, so that's the statistical computational gap. We know that information theoretically, like when k is even moderately large, and we'll get back to how large it needs to be exactly, you can tell the 2 distributions apart very likely, but computationally, this click is very hard to detect up until it becomes very large. And the question I want to ask today is, how large does it become to be? Does it need to be? What is the answer? How many people know the answer? Yes? Square root of n, right? So it becomes hard at square root of n. And the low-degree method is one way of explaining why it becomes hard at square root of n. Okay? And there is this, what I'm going to do is, like most of what I know and what I learned is taken from this wonderful survey by Kuniski, Bandera, and Wine, where they explain this method. So this is the idea. The idea is that we're going to ask, well, suppose that you wanted to distinguish between these 2 distributions. What would you do? Like, how would your distinguisher look like? What would you try to do? Well, one thing that we can do is we can count edges. Right? We can say, well, the click that was planted, it induced some excess of edges in the graph. And the way that we'll try to distinguish these 2 distributions is just by counting how many edges there are in the null distribution and how many edges there are in the planted distribution. So this is the counting edge algorithm. The time complexity of this algorithm is linear, right? If I have a graph on n vertices and n squared edges, it's going to be very close to n squared. And what is the distinguishing advantage that this algorithm has? Well, to figure this out, we have to calculate how many edges there are in the null distributions and how many there are in the planted distribution. In the null distribution, the number of edges is a random variable, but it's a binomial random variable, right? And it's a bit easier to count of edges and non-edges as +1 and -1, so that they cancel out, right? And then the excess, or like lack of edges that you have in this graph is going to be on the order of the standard deviation. There are n squared possible edges, or n choose 2 possible edges. So it's going to be about plus minus theta of n, because n is the square root of n squared, right? So this is what we would expect when we see a random graph. It's going to have about n choose 2 plus minus theta of n edges. What about the planted one? Well, in the planted distribution, on top of this, now I put in this clique inside. This clique has size k, so I'm going to have an extra k choose 2 edges, right, which is going to be theta of k squared. Okay? And what this says is that, well, as long as this k squared exceeds the typical fluctuation in the number of edges in the random graph, then I can be confident and distinguish between these two distributions. So what this says is that at least when k is bigger than, when k squared is bigger than n, I know that I can distinguish and that the edge distinguisher works. And you might say, well, what if k now is less than square root of n? Because this is the regime we care about hardness. Well, this says that this still gives you some advantage in distinguishing, right? So we know that the advantage of this distinguisher would be, you can calculate it, it's like some ratio between k squared and n. And now we can start asking the question, well, is this the best I can do? Right? If the clique has size less than square root of n, is this the best I can do? Okay, so that's just one algorithm. What's another algorithm for distinguishing? Another algorithm that you can try doing is, well, instead of looking at just the edges, I'm going to try to count like some larger features in these subgraphs. And the feature I want to focus on is cliques, but not cliques of size square root of n or something like that, but much smaller cliques, cliques of size 3 log n. And why is 3 log n a magic number here? Because as we will see, these kinds of cliques are very unlikely to be present in the random graph, but of course there will be plenty of them. In particular, there will be at least one in the planted graph because we have a much larger clique, right? We already have a clique of size, I don't know, n to the 0.5 minus a little bit, right? So this algorithm actually distinguishes with advantages very close to 1, right? Here the count will be 0, and here the count will be strictly bigger than 0. And what is the complexity of this algorithm? Well, I have to look at all possible cliques of size 3 log n, so the complexity is going to be roughly n choose 3 log n, which is super polynomial. For this particular example, I'm going to think of super polynomial as something being hard. Okay, so we have these two algorithms. They're kind of extreme. In one algorithm, we get very simple, right? We get linear time, and it gives you like some distinguishing advantage. And then on the other extreme, we have this other algorithm, which distinguishes perfectly, right? It distinguishes almost always, but you need super polynomial time to calculate it. The low degree method is a method for arguing that, there is nothing in between, that these are the only two strategies that you have to worry about. So how does it argue this? So you have to have a model about what an algorithm does to argue this, right? You have to say what an algorithm does. And the main kind of modeling assumption that you make here is that the way that you argue these things is that you think of a distinguisher as being some low-degree polynomial, right? So in the case of the first algorithm, the low-degree polynomial would just count edges, right? So it's a degree 1 polynomial. The variables of the polynomial are the adjacencies in the graph, so the input is a matrix, and here I'm just going to add up all the entries of this matrix. Okay? What about the second algorithm? When I count cliques, then it's a higher degree polynomial, because there I'm looking for these objects, the planted clique of size 3 log n in the graph, but this planted clique of size 3 log n is a monomial of degree log n squared, because it has 9 log n squared, or whatever, because it has 3 log n squared potential, 3 log n choose 2 potential adjacencies between the edges. So they're both polynomials, but the first one is a low-degree polynomial, and the second one is a substantially higher degree polynomial. So that's the first kind of modeling assumption that you make, is that the kinds of algorithms I think of are going to be some polynomials, but then what do I do with the value of this polynomial? Well, the way that we think about when our distinguisher works is that we have to look at two things. We have to look at the average value of this polynomial, which is the calculation that we did, and then we have to look at the standard deviation. In this case, we were looking about the standard deviation under the null distribution. So kind of a necessary criterion for this kind of analysis to go through, to say that my distinguisher works, you should say that at least the averages between these two distributions should be well separated. How well separated should they be? By at least some standard deviation or some small number of standard deviation. And here I'm going to focus on the standard deviation under the null distribution. If you actually want to turn this into a proof, you also have to worry about the standard deviation under the planted distribution, but the low degree method does not do that because somehow the point of the method is to prove a lower bound, not an upper bound. So what the method is going to say is that in some sense, no matter which polynomial I try, as long as my polynomial is reasonable, you're not going to get this. You're not going to get a sufficiently large gap between the two statistics, between the value of the polynomial under one distribution or another distribution. And why is that? And how do we argue it? So here is the reason why this is true, is because this is the fundamental theorem of low degree analysis, is that it turns out that the best advantage that any degree D polynomial can give you has a geometric interpretation, and I will tell you what this is. I don't want to get into too much terminology, but essentially, I mean, the way that, when we talk about statistical distinguisher, what do we look at? We compare the likelihoods under the planted and the null distribution. So you can capture this likelihood in the likelihood ratio. I divide the two, okay? And if I do a statistical test, I want to know like whether one is large and the other one is small, so it depends on whether this ratio is large or small. And this tells us that now, if I don't have all the time in the world, if I want to distinguish by some like low degree test, then the best I can do with respect to this kind of criterion is the degree D projection of this likelihood ratio. This likelihood ratio is a function. It's a function of the adjacency matrix of the graph in this case. And what I need to do is I need to project this function on the subspace of degree D polynomials. And there is a -1 there, which is not too important for us. And what is the consequence of this for clique, or for a problem like clique, is that all we have to do is now we have to calculate the degree D projection of the likelihood ratio, which sounds like a crazy thing, but it turns out it's not. So I'm going to do that next. And when we'll calculate it, we'll see that it's actually, it's going to be large when the degree of the polynomial is log n squared, which means that these cliques of size 3 log n will start to dominate. But if you stay below that, then the likelihood ratio, the degree D projection will remain small. So in the case of clique, what this analysis tells you is that all the way up to degree about log n squared, divided by some fudge factor log n over there, you cannot do better than just counting edges. You can try to count triangles, you can try to do this and try to do that. No, it's not going to help you. Counting edges is the best that you can do. And I think this is very interesting, right? It tells us that among some class of algorithms, like the simple one, the one that came first to your mind, is the best possible. Okay, so now comes the real fun part. Like, how do you actually do it? How do you do this calculation? And that's where the geometry really plays a role. So what's a degree D projection of some function? It could be the likelihood ratio, it could be anything. So, well, you think of the function as a vector in some like 2 to the n choose 2 dimensional space, right? You have one possible value for each possible graph. And the projection of this function is just like some vector that I get when I project it onto the subspace that's spanned by some low degree polynomials. Well, how am I going to calculate this projection? And if you've done a bit of Fourier analysis, you know that there is no better basis but the Fourier basis for calculating projections on the space of low degree polynomial. It's a very natural basis that spans the space of polynomials. And when we do the calculation, you get that the value of the projection, which is the likelihood ratio, is actually going to be, when you square it, the sum of the low degree Fourier coefficients of the likelihood ratio. Okay? So even if you don't know what it means, like you see a nice formula like this and you say, well, this is probably something I can handle if I read about it. And you read up about it, and what is this Fourier coefficient of the likelihood ratio? It turns out it's very nice. It's nothing else but the average of the XOR function, the parity. So I take some subset of edges, and then I see under the planted distribution, what happens if I calculate the XOR of these edges, like the presence or the absence of these edges. Under the null distribution, this would be 0, right? Because every one of them is equally likely to be an edge and a non-edge. And it says all I have to do to figure out how far I am from the the null distribution is to calculate the parity. And in the case of clique, what does this mean? Well, you know, I have some subset of the edges. Now I cover them up with this random clique, right? If the clique doesn't happen to cover these edges, then this parity will fluctuate because the remainder of the graph, the one that's not covered by the clique, is completely random. So all you have to do is you have to calculate the probability that it's 1, which is the probability that the planted clique covers the subset of the edges. And this is not a difficult calculation, as you can imagine. Just to show you, I wanted to do this calculation for the case when I have exactly one edge. So what happens here is that I have this one edge here, and the chances that it's covered by the clique, it's going to be something like k over n squared, right? Because each one of these endpoints ends up in the clique with probability k over n. And now all I have to do is I have to count, right? I have to square this whole thing, because that's what the formula tells me. And I have to add a bunch of terms, right? One for each, what am I doing here? One for each subset S. So I'm going to add these terms for subsets of size 1. How many of them are there? There, and choose 2 of them. Okay? And if you do this calculation, you end up with something that looks like k to the 4 divided by n squared. This is the projection squared. If I take the square root of that, if I look at just the projection, the likelihood ratio, it's k squared over n. What does this formula tell us? It tells us exactly what's going on with the edge distinguisher. When k squared is bigger than n, then the likelihood ratio blows up, like the low degree projection blows up, and I can distinguish. And when k is less than square root of n, in fact, this captures the advantage of the algorithm. It tells us that this is the kind of advantage that we expect. And this is exactly what the low degree method gives us. Yeah, so in this case, it's just a simple calculation. In some cases, it's a more complicated calculation, but they're always very fun to do. Okay, so now comes the one part, well, two parts. The one, no, not yet. So I want to say, well, okay, so what's the take-home message? Why should I learn about this? Why bother? Well, let me tell you about first what I think is good about it, and then what I think is problematic about it, and then you can pick which side you're on. So what does this kind of analysis capture? It captures counting small features, like edges, small cliques, cycles, or something like that in the case of clique, okay? And you can say, well, this is not a lot, right? My algorithms are more powerful than that. But it turns out that it does capture many interesting things. So for example, one thing that you can say is, well, suppose that I'm not only interested in calculating the expected number of triangles, but I also want to calculate the standard deviation or the variance. It turns out that the variance of a low-degree polynomial is also a low-degree polynomial. And if you've done these calculations, you know why. Because if I now try to calculate the variance of the number of triangles in the random graph, essentially I end up taking a linear combination of some objects like pairs of triangles that intersect by an edge or something like that. So kind of linear combination of low-degree statistics are also low-degree statistics and are kind of higher-degree statistics, right? And that's one reason why the method is actually more powerful than it may look at first glance. Also, well, you know, this kind of thing, you know, clicks in graphs, if you like do spectral graph theory or things, this is, you know, the first example of spectral graph theory. Does this capture it? To some extent it does. Because, well, again, like you have to be careful about exactly, now you have to start doing bin counting, but if you at a high level, what happens is that if I calculate, say, the eigenvalue, or I want to calculate the top eigenvalue of the adjacency matrix, essentially to lower order terms is the same as counting some loops in the graph that are not too large. So if you haven't seen it, it's not too important, right? So those are, I think, two kind of nice features of this method. And the third nice feature is that it lets us reason about problems where the best distinguisher, the efficient distinguisher has noticeable advantage. And many techniques in crypto struggle in this regime, right? So if you try to do reductions in the regime of noticeable advantage, they don't compose very well. Right? If I have the distinguisher that works with advantage 1 over n or 1 over square root of n, I cannot compose it more than n times, because then the advantage blows up. The low degree method has no issue with that. It's practically designed for these kinds of problems. And a lot of the problems I showed you on the picture, they do have this kind of feature that, the advantage is that you cannot expect to get exponentially lower non-negligible advantage. What are the drawbacks? Well, the first drawback is what I told you, like the other algorithm, Gaussian elimination, passes with flying colors, right? It's completely fooled by things like bounded independence. And then you have to, once you get into the specifics, you have to start wondering, well, what do these results really mean? So for example, here I told you that, clique is secure up to degree log squared n. What does this mean? Like, what is the algorithm? Well, it turns out that degree log squared n is not the same as time 2 to the log squared n. It's the same as time 2 to the log n. Sorry, it's what did I want to say? You have to worry about what these trade-offs mean. I don't want to get into more detail. And that's a bit problem-specific, right? Sometimes, like exactly how an efficient algorithm translates to a degree bound is something that you have to, like there is no general rule that tells you that. Okay, so we're crypto people, right? We want to know, well, okay, now I want to know. I want a theorem that tells me when is something secure, right? Say I did my low degree calculation, how do I know that I'm right? And if you want a specific conjecture, there is this conjecture of Hopkins, which I don't completely even know how to state it, but the gist of it, from what I understand, is that if you want to fool the low degree method, you need 3 ingredients. A, you need high degree, so you need to make sure that the low degree tests have small advantage. B, you need some amount of symmetry. Like, so the clique problem has it because it's symmetric under permutation of the vertices. So somehow the size of the symmetry group on like the planted distribution plays a role. And C, you need some noise just to fool Gaussian elimination, right? And he conjectured that as long as you have those 3, then this is a good predictor of what it means for something to be for it to be secure. Okay, and I'll leave it at that. Right, there is kind of some arguments about whether this is true and to what extent we can trust it, but at least it gives you a starting point to think about what does it really mean when I prove that something is low degree secure. Yes? Yes?
That you cannot break?
There is, but I don't know it. So it's in some Hopkins thesis. So yeah, you have to look at it there. And I think the way it was stated, like that exact version was disproved maybe by Holgram and Wine. I don't know. There is some story there, but you have to read it on your own.
So there are several statements of this form that were broken in the past. So I think that we should be careful.
I think there is one statement. There is not so much disagreement about what it should say, but like exactly like how the parameters and the hardness relate, maybe there is some disagreement there. I don't know. Okay. Yeah. This is too much. I don't know that much. Okay. So, okay, so that's a good question. Anyone else want to ask about low degree? Because I want to tell you about the other exciting thing. Okay. No. Crypto. I didn't do any crypto. Right? So, okay. So, Benny, good. So, what is the application to crypto? And the application is that there is this wonderful proposal of a public key encryption by Applebaum, Barak, and Wigderson, way ahead of their time, 2009, that I'm not going to even explain to you how it works, but I'm going to tell you what their public key is. Okay, so what is their public key? Their public key is they take not a dense graph like the one for clique, but they take a sparse bipartite graph or hypergraph, whatever which you want to look at it. So you have some kind of sparse graph with some vertices on the left, vertices on the right, very few edges in between. And then what you do with this graph is you plant something inside it. And the object you found is what's like, now we like to call a hyperloop. It's like this small subgraph that has low degree on the right. Everything has degree 3 on the right, say. But what's special about the hyperloop is that it has even degree on the left. And somehow this even degree allows you to do cancellations modulo 2 when you multiply it by something, right? And now you can ask, well, can you see this hyperloop that you planted in the graph? Can you distinguish it or not? And we don't know how to do it. How do we argue that we don't know how to do it? And that's pretty much tailored for the low degree method. And we have a work last year which is actually argues that a random graph with a hyperloop planted in it is low degree indistinguishable from a random graph. And in fact, I should give more credit to Applebaum, Barak, and Wigderson, because even before there was a low degree method, they pretty much did some of this calculation themselves. So they calculated small subgraphs and everything. The low degree method gives you kind of a nice, elegant way of doing the whole calculation in one shot. And why is this useful? Well, one thing it's useful is we found that when we try to understand this crypto system, you can ask, somehow this hyperloop allows you to decrypt, but there is some decryption error. And the way that you might think of handling this decryption error is by planting more hyperloops. Is it secure to plant more hyperloops? And it's a non-trivial question precisely because we're in this regime where there is noticeable advantage of breaking the crypto. And it turns out that how you pick the hyperloops is then relevant. If you happen to plant the same hyperloop many times, then it turns out it's insecure. And the low degree method tells you this, that if I now take this and then I plant the same hyperloop too many times, then it becomes insecure. But if I plant many independent hyperloops, then it remains secure. And how would you know this unless you have either great intuition or you have some framework to understand it, and the low degree method provides exactly this. Okay. I thought I would have a lot of time, but I want to tell you about this second exciting method that comes from, I guess, partly from the statistical physics community, partly from now statistics and machine learning, and it's something called the overlap gap property. Okay. So now I'm going to take a different variant of the clique problem. I'm going to forget about planted clique, and I'm just going to take a random graph. What is the size of the largest clique in the random graph? Does anyone know what this number is? So there will be a clique of size log n, but it turns out that the largest clique will typically be a little bit larger than size log n. It's going to have size 2 log n. Okay? And that's what happens when you have a random graph. And now you can ask the question, how am I going to find this clique? How am I going to find this clique of size 2 log n in a random graph? That's another kind of fascinating problem, old problem in average case complexity. We don't have algorithms, so we believe that this might be hard. How do we argue that it is hard? And now, there is kind of how you're going to think about this. And there is this viewpoint which is a little bit alien when you come from complexity theory, but apparently is very natural from the physics community. And now, again, what I'm going to tell you, there is this wonderful survey. So this has been going on for a long time, but it's kind of come into theoretical CS, more widely known lately. And I learned about it by reading this great survey of Gamarnik, where he tries to explain it. And he credits the method to Mézard, Mora, and Zekina, or the name at least of this overlap gap property. Not the name. They invented the name, but the idea. I should say the idea to it. So what is the idea? So the idea is how might you go about finding this clique? And one way you might go about it is try to set up some kind of physical system. So I want to associate some energy to different cliques so that smaller cliques have lower energy and, higher energy, and larger cliques have lower energy. And now I might want to do some kind of greedy search or random walk where I start with a single edge, and then I try to kind of augment it towards something larger, add more edges to it, so that in the end I end up with some clique which is fairly large, of size 2 log n or 1.9 log n or something like that. And then you might ask, what might happen to my algorithm? And your intuition might be, oh, this is not going to work, but why doesn't it work? The way they think about it is, well, we think about kind of the landscape. So if we run these algorithms, there are two things that might happen. Somehow the desirable thing is that there is this valley of large cliques, and then if we do some kind of, local search or Monte Carlo or some kind of gradient descent, we might hope to end up in this valley. But how do you know that you then don't end up in this situation here? What is this situation? Maybe you ended up with this small clique in the middle, and somehow you cannot get out of it. To get to the next two largest clique, you have to kind of overcome some barrier. You have to change a lot of things. And the overlap gap property is a precise way to capture this kind of hardness and what is going on here. And it has this fascinating relation to algorithms that I hope to tell you about. So what is it? This is what it says. Imagine this humongous graph where the vertices of the graph are the objects you try to find. The clicks of size, let's not make it 2 log n, let's say 1.9 log n, right? And I'm going to put an edge between any 2 clicks that are nearby. So if I can move from one click to another by changing few edges, so I have this click here and this click here, and they have large overlap. They overlap in a lot of edges. I'm going to put an edge between them, right? And I can create this humongous graph of all my clicks in my random graph, the disorder, right? That's what the physicists call the disorder. Okay, and now somehow what it says is, well, I start with a graph on one side, right? And no, I look at this big graph, and I want to know, like, whether this graph is connected or not. Whether if I start moving from one graph on one side and I want to reach another click on the other side, whether I can make it through, right? And the overlap gap property says that you cannot make it through for a specific reason, and the specific reason is that there do not exist any pair of clicks anywhere in the graph that have a medium overlap. A click can overlap with itself, so it always have large overlap objects, or you can have like one large click here and one large click there, so you can have things with very small overlap. And what the overlap gap property says is that you don't have anything in the middle. So there is this middle range of overlaps, like clicks of size 1.8 to 1.9k. Pairs of clicks that have this overlap do not exist anywhere in the graph. And this is what the overlap gap property says, and this is an obstacle for various class of algorithms. So now, in my remaining time, I want to show you 2 things. I want to kind of give you an idea first about why we expect a graph, why we expect the overlap gap property to hold, and B, what is the connection with algorithms? Why is it that if a problem has this property that it's hard for algorithms? And here is the other calculation I wanted to do. So one way to understand this is you have to do some counting. So you take a random graph. Now we're counting natural clicks. What is the expected number of clicks in a random graph where there are n choose k possible clicks of size k, and each click is present with probability 2 to the minus k choose 2. Okay, so this is the calculation you would do. And this becomes like, so at some point it goes below 0. Where is the point where it goes below 0? So the point where it becomes 0 is precisely when k is about 2 log n. Okay, I don't have time to do the whole calculation. You have to trust me on this. So we know that, like if we kind of grow the size of the click that we try to find, 1.8 log n there will still be plenty, 1.9 log n there will still be plenty, at 2 log n they vanish. So now suppose that I'm looking for this kind of very large click. Okay, how many other clicks are there that have large overlap with it? So given that I have a large click, a click of size k, about 2 log n or 1.9 log n, how many other clicks are there that share most of the edges with it? Like this is my click k prime. Okay, so they're kind of, I have to remove one vertex from the original click. I have k vertices to remove. I have to add one new vertex in the new click. There are n extra vertices. And now I have to make sure that this new vertex is connected to all but one vertices in the old click. And this probability is 2 to the minus k, maybe plus 1, because I have an extra vertex here. And the point is that when k is about 2 log n, this is much, much less than 1. It's about 1 over n or something like that. Which means that kind of, if I look at, I have a click. If I look at the number of clicks that overlap with me in almost all edges, this number already goes down by n from the total number of clicks. So now if I look at, like, if I reduce the size of the overlap a bit more, what you end up with is some curve that, like, you start with many clicks here, but very soon you shoot down all the way to 0. And at some point, you just don't have it overlap. Like, they vanish. So it's just some, like, not too difficult calculation that you do. And with this calculation, it says it, even on average, you're not going to have too many pairs of such clicks in the graph. Okay, so that's the calculational part that tells you why you can actually figure out whether it holds or not. What does it have to do with algorithms? And here is sort of, so, there is this intuition coming maybe from physics, why this is hard for algorithms, but I like the way that it was explained. Like, I think this is an idea that was first in Gamarnik and Sudan, and it's explained, like, worked out kind of more rigorously, I would say, in later work. And this is the idea. The idea is now you start with a random instance, and you evolve it. Like, you re-randomize every edge in your random graph I take this first edge, I re-randomize it. Maybe it stays, maybe it doesn't. I take the second edge, I re-randomize it. Maybe it stays, maybe it doesn't. What do I get in the end? After I've done this for all my and choose two edges, I get some graph which is completely independent from the one that I started. So I get two completely independent graphs. And now, it turns out that this OGP extended gives you something called the ensemble OGP, which I don't have time to explain in detail, but it says that not only does every single graph in this sequence have OGP, but even if I take the graph I started with, I look at all possible clicks in this graph, and I take, say, the 10th graph in this sequence, all possible clicks in that graph, no click here is largely overlapping with a click in the first graph. It's essentially the same calculation. Turns out that the most difficult case is when you look at self-overlap, right? So it has this property. And why is this relevant? Well, it says that somehow, like, these graphs, you know, like, if I now walk through this sequence, right, now I have to kind of, it won't make much sense, but I have to think of kind of a dynamic version of this graph, where, say, I start here, then I take one step of the algorithm. So not only do I change the click, but I also change the input. Maybe I end up here. Then I take the second step. So again, I change something. And what ensemble OGP tells me is that I can never jump from here to here, because that would require going over the medium range of overlaps, which is forbidden. On the other hand, it turns out that if I take two random graphs, the initial and the starting one, it's very likely that their clicks will have very low overlap, so that I have to jump to go from one to the other. So that's what forbids the algorithm from doing it. What kind of algorithms does this work for? Well, let me skip the calculations. This is an example of an input local algorithm. Like, if the algorithm has the property that every time I change an edge in the input, I cannot change too many edges in the output, then I cannot go over the jump, right? So that's like a very rudimentary class of algorithms. It turns out you can extend the same idea to output local algorithms as well, which is much more natural, right? I'm not going to do the calculation here because I want to save some time for the end. But you can do the same argument, like it's very nice. And you can also do it, like if you're a complexity theorist, you might have more appreciation for this, or if you have done things, for bounded depth circuits. So it turns out that any algorithm that doesn't have too much sensitivity in the input, that if I change a random input, not too many output change, like there is a variant of this argument that tells you that this algorithm is, well, unlikely to succeed with some ifs and buts. Okay, so instead of going over this in detail, I will tell you a kind of theorem that you can prove using this technology. So this is a kind of theorem that's proved in their paper, is that if I take a random graph, it turns out they cannot quite do it with edge probability 1/2, but some edge probability which is not too small. Then finding a click of size slightly larger than half the size of the largest click, you cannot do it in bounded depth and polynomial size. So it requires super polynomial size circuits of bounded depth. Turns out this 0.5 is for some reason optimal. You can actually do it if you go a little bit below it. So it's tight in some ways. Okay? And I think this is exciting because at least I don't know any other way of proving this, right? So the overlap gap property actually gives you a way to prove a complexity theory result, which I think we don't know how to prove in any other way. What is the relevance for, okay, let me go over the laundry list and tell you a bit about the relevance for crypto. What is great about overlap gap? You can prove algorithmic hardness for classes of algorithms, like input local, output local, AC0. Calculations are fun. We got to do one. They get even more fun if you get to do more. There is a connection to this replica method from statistical physics, which I want to say a few words about. And there is also, like, if your calculation fails, it turns out it's not the end of the world because there are many natural versions you can try, like multi-overlap gap property, that might work. What are the negatives? It's fooled by modular linear equations, like Gaussian elimination is not handled at all. Now it's even trickier. There are some other exceptions also, which I don't know that much about, but you can ask the physicists. One thing that this I'm really not sure about, so it's that it seems to me that it works well when the distribution itself is like a product distribution, but when you start dealing with planted instances, then it seems to me it's a bit less effective, but that might be more owing to my own misunderstanding of the method than to actual obstacles. And okay, the last one is that I didn't get into it, it's a finer point, it only rules out algorithms that are very likely to succeed. Okay, so I'll tell you a bit about the crypto connection. I'll skip this fascinating part. Ask me a question later. And I will tell you a bit about this work that we try to do that tries to exploit this property to actually prove something cryptographic. And what does this have to do? This has to do with something called the binary perceptron. And this is an ongoing project with a large group of pretty much the whole Bocconi CS department, like many of them are physicists here. And because some of them invented this, so it is called the binary perceptron, they asked the following question. So it should look familiar to us cryptographers, but the setup is a bit different. I take a matrix of Gaussians, like random Gaussians. I hit it with a +-1 vector. I get some real numbers, and then I round them. So I just take the +1 if it's positive and -1 if it's negative. So they ask the question, like, if I pick the right-hand side at random, then does it have a solution? And if you do the calculation, like first moment calculation, you would say, well, roughly you would expect a solution when the right-hand side and the left-hand side are the same. And it turns out this is wrong. And it's wrong for a very interesting reason, that the first time solutions appear is that when the left-hand side is like about 0.8 times of the right-hand side. Or maybe it's the other way around. The right-hand side is like shorter than the left-hand side. And Alon and Nikolai had this wonderful idea. It says, well, this looks like it's shrinking, right? Is it collision resistant? Like shrinking things are collision resistant. And this led to this fascinating question about whether this kind of construction is collision resistant. And it turns out that you can formulate it in OGP language, but it's a problem that from the physics perspective is very unnatural. So the physicists never asked it. It took like a cryptographic motivation to ask this problem. And to cut the suspense short, like the answer is it collision resistant? Probably not. But we don't know for sure. How do we know it's probably not? Because our physicist friend ran experiment with their latest algorithms and they find collisions. Okay? Okay, so what happens if we change the activation function, make it more jagged? Well, then you have to start worrying about order of quantifiers and such things, which our physicist friends are not too concerned about. So we had to do analysis. And then we think that it's probably also not secure, not collision resistant, for reasons I don't explain. Now you say, well, what if we disallow collisions that are really close to one another, like strings that match in 99% of the coordinate? And then we think that the answer should be yes. Okay? And why do we think the answer should be yes? We think it should be yes because it has overlap gap property. And that's a conjecture, and we're still working, like after a long time, I think proving is out of reach, but at least getting good evidence why this conjecture should be true. So that's the connection I wanted to say about cryptography. Okay, so how much time do I have? Am I done? I'm finished? Or? Okay, I can take a little bit more. Yeah, so I want to spend the last few minutes to kind of say, well, why is this interesting? You know, we can do amazing crypto with DDH, LW, LPN, you name it. Why bother with these things, right? They give you like very bad things like noticeable errors. Why bother with them? And my answer is because computation has changed. We live in the age of machine learning, and we have to adapt to the age of machine learning. And I think as theoreticians, you know, like some of us have been, well, some communities have been more successful than others. And this is my grade about how I think each of our communities has adapted to the age of machine learning, right? And I'm not going to, you know, algorithms, I don't do it, so maybe I have a rosy view, so I give them a high grade. Complexity, I'm very strict with. I think they have adapted very poorly to the age of machine learning. Crypto, I think, has done very well in figuring out how crypto can help, you know, for securing, you know, privacy and all these things. But the foundations, not so much. And that's the part that I'm interested in, is the foundations. And what does this have to do with foundations? Well, remember, there are two algorithms. There is Gaussian elimination and gradient descent, and we handle both. But if you talk to a machine learning person, what they will tell you is maybe Gaussian elimination is just like a tiny bump in the, you know, unstoppable march of gradient descent. How do you know that eventually, you know, general artificial intelligence, they're not going to be able to find some I don't know, 760-dimensional manifold representation of modular 2 Gaussian elimination, and you run gradient descent, and boom, there goes your LPN and LW and whatnot. Okay? And I don't believe that. I don't think many of you believe that. But if I had to bet my money on whether this happens or a quantum computer happens, I would think about it, right? And we do so much work. We do so much work preparing for the post-quantum age. How much work did we do preparing for the post-AGI age, right? And I think there is a lot of opportunity here, right? We have these kind of things we're very confident in. We can build crypto. But there is this whole kind of sea of other problems that we don't really understand. Like, they give us, these kind of techniques tell us that there is something interesting going on. They're average case hard. We can build one-way functions out of them. We can, in principle, get pseudo-randomness out of all these things. But how do we do it, right? And I'm particularly interested in like these kinds of problems, a lot of them that come, I think one big contribution of statistics and machine learning is they gave us many more examples of average case problems to think about. Right? Before we had 3 examples, now we have 30 or even more. And many of these examples work with real numbers, and I don't even know how to say this, but kind of developing some kind of cryptographic theory for problems that work with real numbers, I think is a really, really interesting question that we still don't know. We don't have anything to say about it. So thanks for being patient, so I will end here.
Sorry, wait for the mic, otherwise people who cannot.
Thank you. So for this perceptron problem that you mentioned,
yes.
So you have this random matrix A with Gaussian
yes.
entries, then a short input X, and then you're taking the sign as the output.
Yes, it's a plus minus 1.
And
yes.
you're saying that if it's compressing, then you were asking, is it hard, is it collision resistant?
Exactly, yes.
Now, if instead of rounding this by taking the sign of the output, you take the output modulo Q. So this is the SIS, the lattice, standard lattice problem, which is building hard, the average. So what is your intuition about?
So it's about the fine print a lot of the time and the order of the quantifiers. So even when you do it modulo Q, it's like Q has to grow with the input size. So somehow, like from the statistical physics regime, it's more natural to think of all the parameters as fixed and the input size growing. So that's the regime that we have been looking at. So I fix everything. Like I change the activation function. Maybe I take something more complicated, but I set this like in stone, and then I let n go to infinity. And that's what we're looking at. And we're just not sure. Like it seems that if you look at collisions that are nearby, they seem easy to find for reasons we can't quite explain yet. But if you look at slightly, like things that are slightly apart, then it becomes hard to find. And we don't know. I mean, it could be that we don't know enough about lattices and all these things, and there is a reduction. I think there is some exciting papers in this very conference that do such reductions, so maybe you can explain it. But in any case, we want to explain it using OGP, right? So that was part of the goal of this project. Excellent question. Yes.
Andrej, can you tell us about Parisi's zeroth moment method?
Thank you so much for asking that question. Okay, this is great. This is my favorite. Okay. So in the planted clique, not planted clique, in the natural clique, how do we actually know that the cliques are even in there? We calculated the expected number, right? But to know that they're really in there, you need to also calculate the variance, right? If you want if you know that if you want to show something exists, you want to show that you have something that's at least some number of standard deviations above the expectation. So we need to do a variance calculation, which I swept under the rug and I didn't do. And so the common tool of doing this is the second moment method. I calculate the expected number, I calculate the variance, and I show concentration. That the variance is concentrated around the expectation. Namely, the first term, the expectation dominates the variance. So what do I have to do this? I have to calculate some covariances, and I have to do their small. So I'm not going to say what replicas are. Ask me about that later. So but now the interesting question happens, what if this method fails? Here it works. For click, it works. But for this other problem I told you about, it fails. The second moment is much larger than the first moment. So what do you do then? Right? And it turns out that the reason it's larger than the first moment is that the first moment doesn't make the correct prediction. So what makes the correct prediction? And here comes, I don't know if Parisi is the right person to credit this. Maybe Mark will tell us. Yes, okay, it's Parisi. He says, don't look at the first moment, look at the 0.5th moment. Okay? It turns out that the first moment could be concentrated around the 0.5th moment, even if the second moment is not concentrated. But how do I calculate this? How do I calculate the fractional moment? And this is what they tell us. You calculate the first moment, we know how to do. Calculate the second moment, you know how to do. You calculate the third moment. Turns out it's tricky, but you can pull it off if you make something called an ansatz. And you draw this curve of all the integer moments. Okay? And now I plot this curve through these moments here, and then I look at what I get here. Okay? And that's how you calculate it. Okay? And if I can do the half moment, then I can also do the 0th moment. This is like this strange limit when n goes to 0. And it turns out that that tells you everything you want to know. That's what's called the free energy. Then you don't even need to worry about other moments. Like it's unbounded random variable. Okay? So it's kind of this like cheeky way of doing it, right? Where you don't do it the way you're supposed to, but I think it makes a lot of sense. Doesn't it?
And this is not a heuristic, right? This is not a heuristic, is it? This actually works.
The physicists say it works, and in the example where it has worked and made unbelievable predictions, in many of them, you do like 300, 400 pages of math paper, and then they confirm it like years later or something.
I do tell our time. Let's just take one final question.
So, like, in TCS, we also care about like approximation algorithm. So we are searching for like near optimal solution for some optimization problem, right? So I guess it's also like for overlap gap property, you are sort of thinking about like the philosophy, as I understand, is like the nearly optimal solutions are divided in like different clusters. So I'd be interested to see like if there's any connection between hardness of approximation and overlap.
Yeah, so it's for random instances, and there you have to, right, it's in natural random instances even, there is some fluctuation. So even if I look for the exactly largest clique, like if I look for a clique of size exactly 2 log n, then it becomes trickier because the probability that it exists might be like something close to a constant. So even there, I have to work with slightly smaller cliques, like to make sense even of algorithms and everything
constant
here.
Approximation.
Yeah, so there is something inherent about kind of like fudge factors and approximation in this whole methodology, and it is pretty friendly to that. So it works well with notions of approximation. Yes.
All right, let's thank Andrej again.